Module 3, Lesson 4, Boole's Rule. For this module, we'll be discussing the different outlines, starting with numerical integration and the different approximation techniques for your numerical integration using Newton-Cotes integral approximation formulas, specifically the Boole's rule. And then we'll manipulate the formula in order to use multiple application Boole's rule and apply that on a given particular sample problem. The basic concept of an integral of a function is determining the area under your given function curve. Note that approximation of this integral value only works if you end up with what you call a definite integration. A definite integration contains a lower limit value on your integral, which is called a, or in this case, x0, and an upper limit value on your integral, which is often referred to as b, or in this case, x1. The Newton-Cotes integration formulas are the most common numerical integration approximation schemes, whereby the basic theory involves in replacing or transforming any complicated function or even tabulated data with an approximating polynomial function that becomes very easy to integrate. Hence, whatever that complicated function may be, it is simply converted into an nth order interpolating polynomial function. For the Boole's rule, we then apply this same concept, however, converting your complicated function into this time a fourth order interpolating polynomial function, which is then referred to now as either using your Newton's interpolating polynomial function, fourth order, or by using your fourth order Lagrange interpolating polynomial function. This then is the graphical depiction on how your particular technique estimates your given integral value. So from your respective lower limit value all the way to your upper limit value, this technique automatically subdivides your given range or interval limit into 4 equally spaced segments, producing 5 discrete points in order to fit these 5 functions onto a fourth order interpolating polynomial function, and then estimating the area under that fourth order function. Since the technique approximates your integral value under a fourth order function, which eventually would end up like this, if we then integrate this fourth order interpolating function, you would end up with a simplified formula to be equal to this time b minus a multiplied with 7fx0 plus 32fx1 plus 12fx2 plus 32fx3 plus 7fx4 all over 90. However, we note that the Boole's rule approximation formula always requires 5 functions from fx0 to fx4. Therefore, we then use that curve fitting technique in order to estimate that given particular function value. And we know that this particular technique utilizes a minimum of 4 segments to determine those 5 function values. Therefore, your step size would eventually end up with this respective formula, whereby your b minus a is now equivalent to 4h. We could then substitute that into your integral formula in order to simplify our formula further, ending up with a simplified integral approximation formula for your Boole's rule to be this time 2h over 45. Much like the previous integral approximation techniques of the trapezoidal rule, one-third rule, and the Simpson's 3/8 rule, your respective factor or step size h is multiplied by a factor of this time 2 over 45 on your given Boole's rule. And this particular factor of h is multiplied with a pattern of your given particular function, in which case the pattern of our function now becomes 7 multiplied to your fx0 plus 32 multiplying your fx1 plus 12 multiplying your fx2 plus 32 multiplying your fx3 plus 7 multiplying your fx4. This then is the integral estimate for one fourth order interpolating function. However, as we've seen on our previous techniques, like the trapezoidal rule, the 1/3 rule, and the 3/8 rule, in order to further increase accuracy of our integral estimate, we could simply apply a multiple application of this given particular technique. Therefore, under a multiple application Boole's rule, just like your trapezoidal rule, your 1/3 rule, and your Simpson's 3/8 rule, the integral can be further improved by simply dividing the integration interval from a to b using a number of 4 segments of equal width. Each fourth order interpolating polynomial function requires 4 segments with a particular width now and a step size equal to h is equal to b minus a over n, wherein h is the equal spacing between your respective segments, and n now becomes a segment that are multiples of 4, while b remains to be your upper limit value and your a remains to be your lower limit value. Note that when you apply then multiple application Boole's rule on your respective integral, you then add compositely the integral estimate on each fourth order function. And remember, each particular fourth order function always requires 5 points. Therefore, the first fourth order function spans from the limit x0 to x4. The next fourth order function spans from the limit x4 to x8, and so on and so forth. Applying then our respective Boole's rule for each of these individual fourth order function gives us now a formula like this. And you would notice that each fourth order formula eventually has a common factor of 2h over 45, which we can eventually factor out. Factoring out then this common factor 2h over 45 gives us a sequence of our respective function to be now equivalent to multiplying the first and the last function 7 times, multiplying all odd subscript functions to be 32 times, multiplying all even functions with 12 times, and then multiplying all functions that are multiples of 4 14 times, since these are adjacent functions. Or it can be again generally written as this given particular formula. Note that this technique is only applicable for segments whereby these segments are subdivided using multiples of 4. Let's try and evaluate and apply that given particular technique onto our previous example that we have solved using trapezoidal rule, 1/3 rule, and 3/8. But this time, we're going to use Boole's rule at a minimum of 4 segments. At a minimum of 4 segments, your step size would then be equivalent to this solution with a value of 0.2. Therefore, the important values of x, starting from the lower limit value 0 all the way to your upper limit value 0.8, would eventually be x0 equal to 0, x1 equal to 0.2, x2 equal to 0.4, x3 equal to 0.6, and x8 equal to 0.8. Substituting these important values of x onto your given function gives us an fx0 equal to 0.2, an fx1 equal to 1.288, an fx2 equal to 2.456, an fx3 equal to 3.464, and an fx4 equal to 0.232. Applying then our Boole's rule formula, therefore, we'd end up now with a solution now equal to 2 times h, which in this case is 0.2, over 45, with a respective pattern of function this time equal to 7 times 0.2, which is our first function, plus 32 times 1.288, which is an odd function fx1, plus 12 multiplied by 2.456, which is an even function fx2, plus 32 times 3.464, which is an odd function fx3. And finally, the last function is multiplied by 7, which is 7 times 0.232, giving us now a corresponding sum of 184.56 multiplied to our given 2 times 0.2 over 45, thus giving us an integral estimate equal to 1.6405 square units. If we then compare this integral estimate against our trapezoidal rule at 4 segments, we'd end up with an integral estimate of 1.4848. If we then compare that to our Simpson's 1/3 rule at n equal to 4, you'd end up with 1.6235. Unfortunately, we cannot compare this to your Simpson's 3/8 rule since the 3/8 rule is not applicable for n equal to 4 segments. However, we do know that the actual integral value noted on this given particular function is 1.6405, showing us that out of the 3 techniques that we have compared so far at equal to n equal to 4 segments, the Boole's rule turns out to be the most accurate among all 3 techniques. This is due to the fact that our given 5th order polynomial is very much similar to the shape in terms of a curve function equal to a 4th order interpolating polynomial function which spans from 0 to 0.8. Hence, we ended up with a very accurate fit for your 4th order interpolating function, giving us a very, very accurate integral estimate using your Boole's rule. If we then try to estimate using a multiple application Boole's rule now for the next possible segment, which is n equal to 8, onto this given function, our computed step size would then be this solution with a value of 0.1. And the important values of x are as follows, starting from the lower limit value 0, which is denoted to be x0, x1, which is equivalent to 0.1, x2, which is equivalent to 0.2, x3, which is equivalent to 0.3, x4, which is equivalent to 0.4, x5, which is equivalent to 0.5, x6, which is equivalent to 0.6, x7, which is equivalent to 0.7, all the way to your upper limit value, which is x8 equal to 0.8. And then substituting these important values of x to your function gives us an fx0 again equal to 0.2, an fx1 of 1.289, an fx2 of 1.288, an fx3 of 1.607, an fx4 of 2.456, an fx5 of 3.325, an fx6 of 3.464, an fx7 of 2.363, and an fx8 of 0.232. If we substitute then these important values of x onto our respective multiple application Boole's rule formula, we'd end up now with this respective solution, whereby we multiply 2 times your step size h, which is 0.1, and divide that by 45, and apply our respective pattern, multiplying the first function 7 times, which is 7 times 0.02, plus the odd function fx1 32 times, which is 32 times 1.289, plus 12 times the odd functions, which is 12 times fx2 of 1.288, and again 32 of 1.607, and this time 14 of fx4, which is 2.456, a 32 of 2.325, plus 12 times of 3.464, plus 32 times of 2.363, all the way up to your last function, which is 7 times 0.232, upon which we end up with a sum value of 369.008 and an integral estimate this time of 1.64004 square units. Note that when we compare that to our respective trapezoidal rule answer, we'd end up with a trapezoidal rule integral estimate for n equal to 8 to be equivalent to 1.6008, showing you that the Boole's rule, which is a curve function, obviously is more accurate than a linear function in estimating your integral value. Whereas for a Simpson's one-third rule, for n equal to a, we ended up with an integral estimate of 1.6395. And we already know that the actual integral value turns out to be 1.6405. Note that the error in your approximation technique, eventually in this case for your Boole's rule, turns out to have a greater value for n equal to 8 as compared to n equal to 4. And as compared, all these corresponding techniques, like the trapezoidal rule, the Simpson's one-third rule, the Simpson's 3/8 rule, as well as the Boole's rule, all have their own respective error truncation formula. This error truncation formula eventually affects their respective result. Thus, the only technique usually applied in order to compensate for that respective error is to simply increase the number of segments that you can apply on this given technique, making use of multiple applications of these different techniques that were aforementioned. Likewise, like your trapezoidal rule, your one-third rule, your 3/8 rule, and this time for your Boole's rule, you could also tabulate a summary of your respective solution like this and solve for your integral estimate. This ends Module 3, Lesson 4.